Okay, so unfortunately, I'll not be able to talk about any graphs because I know this is what people like here. Things are mostly continuous. The things that I'll talk about. That's true. That is true. Okay, so I'm going to talk about Brownian loop soups. I'll start with the most basic definition of, okay, so this is just the plan of the talk. So what's a loop? So I always work in a simply connected domain in the complex plane, and I'm going to assume that it is bounded. And for one particular result, I'll have to also assume that it is, it has a smooth boundary, but that will come later. Okay, so a loop is just a continuous function from an interval, a compact interval on the real line, 2D, where the starting and the end point are the same. And this T, I'm going to denote a loop with gamma always, and T gamma will be the time length of gamma. And the K of D, this notation just means that this is the set of all loops in D. And so this is just a picture of a loop. And this is what I've drawn. Okay, so loops usually come with a root, and the root is just the starting point or the end point. I want to look at loops that are unrooted, so that loops which do not have root. And the way to do it is by first changing the root. So we can reroute loop gamma by just a shift in time like this. And I'm going to call all the reroutings of the loop, and that forms an equivalence class, an equivalence relation and an equivalence class, and that will for me be an unrooted loop. And I'm going to call it also gamma because why not? And the unrooted loop also is denoted by K of U, and it has a topology on it. It's metrizable, and it has a whole sigma algebra with respect to that topology. Okay, so what's a loop measure? So I fix a T and a Z in the domain, and mu br d z z t, this is a complicated notation, but it's just the law of the Brownian bridge from Z to itself. The bridge has time length T, and the bridge is conditioned to stay inside the domain D. This is a probability measure on KD. K is the space of all rooted loops, just recall. The Brownian loop measure is actually a measure on the space of unrooted loops, and it is defined as the 1/2 pi t square, the mu br z z t. There should be a d here where I'm pointing the pointer, but I've forgotten to add that, so sorry about that. So this is just the loop measure. Okay, so here are some facts. Just stop me if something is unclear anytime. Okay, just. So this is a sigma-finite measure on the space of all unrooted loops, but it has infinite mass, and it has infinite mass because this integral is not finite at 0. So there are a lot of tiny loops. So it gives large mass to tiny loops. So that's the interpretation of this infiniteness. Also, if D is unbounded, then the space of the collection of all unbound large loops that also is infinite. So, but we are not so concerned about that because D for us is bounded. It's one of the most important properties of the loop measure that it is conformally invariant. And I could, I don't want to give a precise description of what conformally invariant is. So here's a picture of a loop and a conformal transformation from one domain D to another domain D prime, and this is the image of the loop gamma. So yeah, just these pictures are just to help populate the imagination, maybe. Okay, so the Brownian loop soup is a Poisson-point process of unrooted loops of intensity lambda times the mu D loop with a positive lambda. And I'm going to denote a Brownian loop soup with L lambda of D. And so because the intensity is a infinite it's an infinite measure, infinite mass. So L lambda will also have infinitely many loops. So in a bounded domain, there will be infinitely many tiny loops in any realization. So again, this is a picture of a realization of a Brownian loop soup. I mean, these loops are obviously not Brownian loops; they're kind of impressionistic picture, but this is what I'm thinking of when I think about Brownian loop soup. So, okay, just for this audience, because people like discrete things, so I'm going to, so there is this thing called random walk loop soup, which is the discrete analog of the Brownian loop soup, and it was introduced by Lawler and Trujillo-Ferreras. Oh, by the way, the Brownian loop soup was obviously introduced by Lawler and Werner, I forgot to mention. And so this is, so one can define an intensity measure, a random walk loop intensity measure. And and if you have a Poisson-point process with the intensity of that, then you can, so a realization of that is called the Brownian random walk loop soup.
I think like this thing will basically like count like the number of, let's say, quote unquote cycles of the random walk takes.
So the random walk loop soup is just a bunch of random walk loops in a domain in Z2 or in a subdomain of that.
Like if it goes like this several times over, it'll count it.
Yeah, you can't count them differently because it's a Poisson-point process, so you can have the same loop twice or more than once. Yes. Especially this is a good question because especially this is important for the case of random walk loop soups. It doesn't really happen for Brownian loop soups, but yes, random walk loop soups is important. So this is just an aside, just to show that there is something called a random walk loop soup, and it does converge to the Brownian loop soup, which was proved by Lawler and Trujillo-Ferreras. The picture is a picture of random walk loop soup. It's not a very nice picture, but whatever. Okay. So the object that I'm going to look at is called the layering by Brownian loops. And so in this slide, I want to convince you that we do not have to look at the entire Brownian loops. It's enough to look at the outer boundaries of the Brownian loops. Okay, so I start with Brownian loop soups. And I want to count the number of loops that cover a point Z in the domain. Obviously, this is going to be infinity, but that's the. So yeah, this is the quantity of interest. And so here I have the same picture of the Brownian loop soup, and this is I have 2 points, Z and W, and here you see that. Z is covered by only one loop, the blue loop, and the W is covered by 2 loops, the green and the red one. And the point is that because Z and W are inside the hull of the loop, I can draw the outer boundary of the loop, and I can only focus on the outer boundaries of the loop. I hope this is clear.
How do we formulate what the set of outer boundaries are? Because we're working in the complex planes, right? I assume any domain, appropriate domain of those could be a possible outer boundary.
So a loop is a subset of the domain. And so the outer boundary is one of the boundaries of the set.
Like inside the outer boundary.
Yes, 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 yes. There is a technical definition of the hull of the loop, and I'm not going to say what that is. But yeah, this is the picture. So the point now is that I can forget about the fine structure inside the loop and just focus on the outer boundaries. And there is a very nice fact that the outer boundaries of Brownian loops are simple loops. So outer boundaries do not cross each other. Okay, so here are some facts about the collection of simple loops. And so say mu d is the measure induced by the loop measure on simple loops, just by drawing outer boundaries. And so it was proved by Werner that mu d is a unique measure up to multiplicative constants, which satisfies the conformal restriction property. And the conformal restriction property just means that it behaves nicely with conformal maps. If I have a domain D and I have a subdomain D prime, then the mu D restricted to D prime would be mu D prime. Okay. And so, yeah, this is what I said. So I'm going to only look at the Poisson point process with intensity lambda mu of D. And I'm going to use the same notation L lambda D. It's an abuse of notation, but still. And I'm going to call it also Brownian loop soup. And so the most important formula, I think.
Like you take some domain here, some domain, then you apply afterwards, and you have some domain prime that you apply.
Yeah, so these are measures, and you have to be careful defining them. So I can write down the precise definition if you want. So if mu d applied to, so A prime is yeah, and so this is going to be all the loops, I think, in the such that okay, and this is, I think, something like that. I think I'm making, okay, maybe an inverse here, but yeah, okay. So something like that. Yeah. Because the intensity is just a mu d, and mu d only gives mass to simple loops. Okay. So so there is a formula which was again proved by Werner, and this is what makes this whole thing possible. So this is the most important formula, is that if I look at loops, again, these are simple loops of diameter between delta and r, and I look at only the loops that covered the point or layered the point z, then this has a precise formula. So this is 1/5 log r over delta. And this is what makes everything tractable. It's just a number. So these are just two numbers, delta and r, and I'm looking at loops of diameter between delta and r. Okay, so as I mentioned, the number of loops that layer a point is going to be infinity. So the way to remedy that is to introduce a cutoff on the diameter, and the cutoff I'm going to call delta. And so A delta is going to be, so this is a notation that I will use. So A delta is going to be the set of loops of diameter greater than delta covering Z. And so here is the first important thing. So I guess the layering number, this is a complicated notation. So it depends on delta, the lambda. Lambda is the intensity, and D is the domain. So the layering number at Z, this is a, so you look at all the loops that cover Z, you flip an independent coin, fair coin, and you assign +1 if it's heads, if you assign -1 if it's tail, and then you sum up those signs. So this is what this summation means. And so I've defined layering number, and now I can define layering field. So the layering field, again, I need some notations. So beta is a real number, delta is just this quantity. Yeah, I don't have anything to say about this, but the layering field is e to the power beta n delta z times delta to the power 2 big delta lambda beta. So that's the main object that I want to study. And okay, so here is a little bit of a background. So this was first considered by Kamiya, Gandolfi, and Kleban, who computed the endpoint correlation functions and showed that the correlation functions are conformally covariant for the imaginary layering field. So this is e to the power I beta n delta of z. So this is the real valued layering field because there is no I here. Here there is. Subsequently, another paper by Kamiya, Gandolfi, Piccati, and Reddy showed that the imaginary layering field converges to something called an imaginary GMC. I haven't defined a GMC, so this is still mysterious. So, but yeah, so that's the result that I'm trying to emulate here, right? And there is another very interesting paper of Vandenberg, Kamiya, and Liss, and they studied the winding field. So the layering field just counts the number of loops that cover a point. The winding field counts all the winding numbers contributed from each of the loops in the loop soup, and this is a much more difficult model to study because you then have to you cannot rely on the outer boundary of the loops. You need to look at the fine structure of the Brownian loops themselves. So as far as I know, there is no similar result for the winding field like the one that I'm going to present, or the one that this paper presented, where the layering field, imaginary layering field, converges to the imaginary GMC. So there is no such result for the winding field. Okay, so I'm going to be very, very brief here, and so I'm going to. So for those who haven't seen, just to be consistent and coherent. So Gaussian free field X is a centered Gaussian process with covariance GD. It's the Green's function. And so it's a log-correlated process, and generally a log-correlated process has covariance like this. So this is log plus 1 over z minus w, gz of w. So just note that this blows up when z and w goes onward, becomes closer, right? So the Gaussian free field only exists in distributional sense. This is not pointwise defined. Yeah, and but there are several ways to approximate the Gaussian free field, and the Gaussian multiplicative chaos is morally it's just the exponential of the Gaussian free field. But again, the problem is that the Gaussian free field is, or any log-correlated field, is not defined as a function. It's defined as a generalized function, so you cannot take the exponential of that. So it's not well defined. So this is where the work of Kahan comes in, and so what Kahan was able to show is that if you can find a sequence of functions xn which approximates x, then you can define this approximating sequence of measures. And okay, and so here's a summary of the result. Well, what we need for our talk. So firstly, this approximating sequence of measure converges to something as n goes to infinity. That something is non-degenerate, so it's not identically 0, only when the parameter is less than 2. And this is a statement about the moments, which I'm not going to need for this talk. But this is an important point to keep in mind, that I can only prove my result in the subcritical phase. Actually, not even the whole subcritical phase, as you will see. Yeah, that's right. Yeah. So this part is just it has a structure of exponential martingales. So this part is not that difficult. I think the more trickier parts are showing that it is something interesting, not non-zero. Also, there is a statement about this M psi being unique in some sense, not depending on the approximating sequence of functions. So I left that out. So those are the more involved parts. Okay. So here are the results. So recall that my Gaussian, my layering field is this object. And so what I've been able to prove, so the results sort of go on for like 4 slides, so just please bear with me. So so I have a bounded simply connected domain with a smooth boundary, and so for a fixed lambda, if I fix the intensity and the parameter beta, then this V delta lambda beta converges to something, and that's something I call a Poisson layering field. As measures in probability. And so for the next result, I need this notation and this terminology. So so I define something called W delta psi, which is so G naught is a Gaussian random measure on the space of simple loops, having the control or the covariance like this. So recall that mu D is the measure which was discovered by Werner. So let's put it this way. And delta psi is just a number, and W delta is it has a structure of exponential martingale. So yeah. So so the second statement of the theorem is that W delta psi also has a limit, which I'm going to call W psi as delta goes to as I remove my cutoffs. Delta. So this is the main part of the, so number 3 statement is the main part of my my results, which is that if I fix psi between 0 and square root 2, so just note that this is not between 0 and 2, this is just between 0 and square root 2. So if I fix a psi between 0 and square root 2, then V lambda beta converges to W psi in the sense of finite dimensional convergence of finite dimensional distributions when lambda beta square converges to psi square and lambda goes to infinity. And the other part of the result is that this W psi that I obtained, it is absolutely continuous with respect to the GMC, and it has this Redon-Nikodym derivative. So if you're wondering what this is, so here's a picture again. So mu D, A dz del D. So this is kind of a zoomed in part of the boundary of the domain, and Z is this point, and it has a distance from the boundary which is dz del D, and this counts all the loops which cover Z but has diameter greater than the distance between Z and the boundary. So this is the term that appears here. And so using this formula, I can show that so the Redon-Nikodym derivative of the Gaussian layering field with respect to the GMC goes to 0. And I interpret this fact as that W psi is singular with respect to the GMC M psi. That completes the results. I have a slide on proofs, and the proof. Okay, maybe I'll present the proof a little bit. So delta. So just the way the exponents were chosen. So delta lambda beta, it converges to this delta psi. So that is how the deltas were chosen, and then the expectation of phi lambda beta of phi converges to. So phi is just a. Yeah, I think I haven't written this. So phi is a continuous bounded function on D. So it's a test function. So v lambda beta, if you test it with phi, and w psi, if you test it with phi, then the expectation of v lambda beta of phi converges to the expectation of w psi of phi. And so the next step of the proof is uses chaos decomposition, Wiener-Ito chaos decomposition, and it just and I can write down, fortunately, I can write down v lambda beta as this infinite series, and w psi of phi as this infinite series, and then the task is to show that each of the terms of the first series is close to the terms of the second series, the corresponding term, and this somehow proves that v lambda beta of phi converges in law to w psi of phi, and then I can use a Kramer-Wald device to prove my result. So that's it. So these are some references that I mentioned, and thank you.
What does this W density signify? Are there similar results in
this W?
No, the next page, the density. So you're having a density with regard to the log-related field, right?
Yes.
So what's the implication of this? That what does it say? It says.
Well, the application of this is the next part. So I'm using this formula to study the behavior of my Gaussian layering field. So W I'm calling the Gaussian layering field with respect to the GMC measure. And so the next result says that as I go close to the boundary, then these two things become more and more singular with respect to each other. So that's.
How should I see it? To the boundary have less.
So yeah. So if you. Yeah, that's.
Loss of entropy?
I don't know. I don't know.
So somehow you're showing that your multiple chaos for GMC.
Yes, GMC.
So not capturing.
Yeah. So. Yeah, I don't know what loss of entropy means. Sorry. So.
Well, loss of entropy means that you have less choices, because once you approach the boundary, you're more constrained. So and entropy means it's essentially about multiplicity of how many loop configurations you have.
Right. Yeah, I don't know.
Initially, I thought it was a Martin boundary type because something else.
No, so one thing that I can say about this is that as far as I know, is that the behavior of the GMC itself near the boundary has not been studied. I didn't really find anything in the literature. So although it does say that the behavior of the Gaussian layering field with respect to the GMC is going to 0, but how does the GMC itself behave? I don't know.
And these loop soups are having a meaning in physics as well. Can you say something about that, or?
Yeah. So I learned most of these things from Federico Camia, and his motivation seems to be that if you have this endpoint functions, then there may be some CFT, like a conformal field theory underneath, which again I don't know anything about CFT, so I really I'm way out of my depth here. So
Okay. Okay, thank you.